Ladies and gentlemen, welcome to the 8th edition of the TSDSI Tech Deep Dive 2025 conference. We're delighted to have you with us from 15 to 18 July. This year's theme is Standardizing 6G, Architecting Intelligent, Secure, and Sustainable Networks and Services. Over the next few days, we'll host 6 online technical sessions focused on global standardization activities and emerging technology trends. On 18 July, we'll come together for a hybrid session in New Delhi, bringing together in person and virtual participants for an enriching exchange. We'll explore 6 critical topics: new network architecture possibilities for 6G, will AI find a critical role in 6G, future path and challenges for integration of non terrestrial and terrestrial networks for 6G communication, security in a hyper-connected world, especially for 6G, management of service delivery architectures, and the OFDM dilemma and potential new waveforms for 6G. On the final day, we'll begin with a workshop on new networks and services aspects of 6G ecosystems, followed by a special session on standardizing 6G way forward. Throughout the conference, we'll highlight the groundbreaking work taking place in TSDSI, featuring research, innovations, and ideas poised to shape future standards. We also invite you to join us either in person or online for the TSDSI OTC Awards ceremony on 18 July as we recognize our experts' contributions to standardization in financial year 24-25. TTDD is more than a conference. It's a platform to share ideas, foster collaboration, and build the future together. We hope you leave with new connections, fresh insights, and a shared vision for 6G. Thank you for being a part of TTDD 2025. Let's begin. I now invite my colleague Shweta Singh to take the proceedings forward. Over to you, Shweta.
Thank you, ma'am. Good afternoon, everyone. Welcome to session 1 on new network architecture possibilities for 6G of TSD Site Tech Deep Dive Conference 2025. I am Sweta Singh, coordinator of this session. Convener of this session is Mr. A.K. Mitra sir. Sri A.K. Mitra sir is associated with TSDSI as advisor with a special focus on standardization in wireless and wireline systems and handled standards related activities of TSDSI in 3GPP and ITUR. Currently, he is working as DG TSDSI. Before I will go over a few hygiene instructions. So these are the few hygiene instructions. So first one is all online attendees except session speakers will be kept on mute throughout the session by default. Second one is kindly post your question in the Q&A tab of the conference tool. These will be taken up during in the Q&A section. And third one is questions in the chat box will not be entertained. Fourth one is if you want to enlarge the presentation, please click on the expanding arrow icon at the top right of the presentation screen. Fifth one is the tool is configured for SD video. You may switch to LD in case you are facing bandwidth problems. Sixth one is attendees may like to visit the exhibit booth of TSDSI in between the session to know more about our work. Seventh one is attendees can use the launch facilities for networking. The launch will remain open till the end of the conference. The conference sessions are being recorded and will be posted to the TTDD website in the next few days. Now I would like to introduce the co-chairs of this session. So Mr. Pranoj Hasar has 20 plus years of R&D experience in communication and networking technologies with expertise in the area of wireless networking. He currently works with IIT Bombay as a senior scientist. His current research interest lies in broadcast broadband convergence, rural broadband communications, and network architecture for 5G and beyond. He has published many research papers and has multiple patents filed and issued. And the second co-chair of this session is Dr. Sonali Garg. So Dr. Sonali Garu obtained her PhD from the IIT Institute, IIT Delhi, focused on low density Pretty check codes. She is currently working with HFCL Limited as senior member of technical staff, where she focuses on standards research and generating steps. The research area of her team is diverse and she is interested in 6G research. Her 6G research focuses on integrated sensing and communication, channel coding and waveform designing and energy efficiency. Now I hand over to Ms. Sonali Garg ma'am for opening remarks and further proceedings.
Good afternoon, everyone. On behalf of the TSDSI and organizing team, as session co-chairs, Pranav and I are honored to welcome you to this important session and the very first session of TTDD 2025 on new network architecture possibilities for 6G. As a young researcher like me, we are honored to have experts under one platform where we can understand the perspective on the area of expertise. And as I know very little in front of all of you, please feel free to correct me with the opening remarks I'm going to present in front of all of you. So, as we look ahead to the 6G era, it is evident that tomorrow's network must go far beyond incremental enhancements. They must be designed to enable immersive communication, integrated sensing, intelligent machine collaboration, and sustainability by design. This shift may demand a complete rethinking of network architecture. That is how we build, manage, and evolve our networks across both core and RAN, spanning terrestrial and non-terrestrial domains and operating across diverse frequency bands. So as we know that 5G introduced several architectural breakthroughs such as service-based architecture in the core, network slicing, capability exposure, and shift to cloud native and disaggregated components. But these innovations also reveal challenges. Some of them we could list like complexity in deployment, evolving security needs, and questions around orchestration and monetization. That brings us to the heart of today's discussion. What should be the 6G architecture look like? Will 6G be an evolution of the 5G blueprint or purpose built for intelligent and sustainable connectivity? How do we architect networks that are not just automated but intent driven, AI native, and compute aware? Or will we retain control and user planes as we know them today, or introduce a service plane to expose programmable capabilities directly to applications and third-party services? And the very important question which comes to my mind is that how do we ensure seamless terrestrial network and non-terrestrial network convergence, ISEC integration, and support for new usage scenarios? To explore these critical questions, we have distinguished keynote address that will set the stage with forward-looking perspective on 6G architectural direction, followed by an expert panel discussion featuring leaders from across industry, academia, and standard bodies. Together, we will deliberate on how architectural innovation can address the technological and societal challenges of the 6G era. We are truly excited to host this thought-provoking exchange of ideas and encourage all of you to engage actively. Ask questions, offer perspective, and think boldly. The future of connectivity starts here, and it starts with the architecture we envision today. Thank you, and let's begin. Shweta, next slide, please. So this is how our session looks like. For the first part of the session, we have 3 keynotes from the 3 experts in the area, followed by the panel discussion where the experts from the industry and academia will deliberate more on the architecture design. Shweta, can we move forward? Yes, thank you. So moving ahead, we will now move ahead with the first keynote session of the day. So with this keynote, we'll invite Mr. Gino Massini, Principal Researcher Ericsson. So Gino is Principal Researcher with Ericsson in Sweden. He joined Ericsson in 1999, working with microwave radio link antennas, network planning, MMIC design, and since 2009, he's working with RAN architecture. Gino is active in 3GPP for more than 15 years. He was elected as RAN 3 chairman for 2 terms, overseeing the standardization of 5G RAN architecture. He received the 3GPP Excellence Award in 2022. He is the author of more than 80 patents, 3 recent books on 5G and NTN, and a number of scientific articles. Gino, we welcome you for today's talk on Towards 6G RAN Architecture, Janus Bifrons, Matryoshka, and Monolith. Over to you, Gino. Thank you.
Thank you very much, Sonali, and good afternoon, ladies and gentlemen. Let me start my presentation. My screen should be visible right now. Thank you. So, towards 6G RAN architecture. So we'll introduce to you some interesting characters, and these characters are pointers to some of the trends that we have identified whenever we talk about standardizing architecture in 3GPP. So I will start by saying, why should we go to a new generation, and what are the forces in play, and why do we do that? Then I will need to say just 2 words on what is architecture. It's a very general word, and sometimes it means different things to different people or group of people. It may even be misused sometimes. Then I will introduce standardization, because this is what it is about today. And then I will simply review the trends and show how they have played from 2G to 6G RAN architecture standardization in 3GPP. Okay, so why should we go to a new generation, a new G? 2G to 3G, 3G to 4G, 4G, 5G, and so on, and now 6G. So over time, new features and solutions emerge. We need to address new use cases and deployment scenarios, and other distinguished speakers will do that. We will hear some of the use cases, deployment scenarios, and things that require new generation. We can exploit technology advancements. So in one word, we need a new generation to address all those things that maybe we haven't invented yet, but will definitely materialize in the future. So the first objection is, but why can't we introduce these new features in 5G specifications or in the 5G RAN architecture or core network architecture? Well, in principle, we could actually, but typically they might not be implemented in practice for reasons such as limited uptake in the UE community, in the user equipment or terminal community. Because, well, typically we have a large fleet of UEs, and these are, for the most part, legacy UEs, and they might not be implementing the new features. And then, probably most important of all, is we have restrictions due to earlier 5G decisions. So if we are trying to shoehorn new features in an older architecture, chances are we might need to settle for suboptimal performance. So in a way, going to a new generation, so 5G to 6G, gives us a very good opportunity to get rid of, let me call it, old baggage, and define a new generation without the legacy that we feel is not needed anymore. But mind you, we still need to ensure a smooth introduction of the new generation. Now, one word about architecture. So architecture may imply different meanings in different contexts. So we may talk about functional architecture, and I would call it which function does what. And in this case, the actions we would do is, well, we start from requirements, use cases, deployments, and so on. We identify the necessary system functions, their interactions, and we categorize them. So then we talk about user network functions, radio, core, and operation and maintenance domain, control, user or data plane, access stratum, non-access stratum, and so on. So this is a functional architecture. Then we have a very powerful concept. We have the logical architecture concept. In this case, we define the required logical functions. One logical function could be user subscription handling. That's a logical function. Or another logical function could be radio resource management. Another logical function could be mobility management, and so on. Then we group these functions into logical nodes. So a logical node is basically a box which is drawn around a list of functions. And then once we have logical nodes, we define the necessary logical interfaces and protocols connecting the logical nodes. So this is typically the task of, in 3GPP at least, this is a typical task of groups such as RAN3, SA2, and RAN2. So whenever we define a new logical architecture, these three groups kick into high gear and start discussing and defining the logical architecture for the new generation. And then, of course, we can also talk about deployment architecture. In this case, this would be what logical node or logical nodes are deployed where. So what follows refers to logical architecture. A word about standardization. A good technical standard ensures compatibility, interoperability, promotes a broader market, and lowers industrial costs. This means it's probably a bit too presumptuous to think that we might standardize logical architectures for each and every use case or for each and every application. Ideally, we should strive, and we most often do strive, for a single architecture to accommodate all possible use cases and deployment scenarios. Of course, we will need to factor in flexibility. We'll need to factor in a few additional characteristics, but we strive for a global technical standard to address as much as possible all the market requirements. Probably one of the earliest examples of global technical standard is shown on that picture in the right. So that's a picture I took of an ancient Roman road in Pompeii. So the arrows points you to a feature that all ancient Roman roads had in basically all around the Roman Empire. Those two tracks were made in order to accommodate the wheels for all carts, carriages, and vehicles. So what this became is a de facto global technical standard. If you were a coach builder in the ancient Roman Empire and you build the wheels of your vehicles according to those tracks, well, your vehicles could circulate anywhere in the Roman Empire. Those tracks ensure that no vehicle could sway regardless of the conditions of the road. So this is, I guess, the earliest possible example we can find of a global technical standard. So what are the trends in logical architecture standards? Well, there's a trend that I identify as atom or monolith, as in the title of this presentation, from the Greek atomos, indivisible. So in ancient atomistic philosophy, the atom was the smallest fundamental indivisible component. So this is a trend towards a self-contained or monolithic architecture. So in this case, we have probably the lower, or there's a trend towards a lower standardization complexity, because all the interactions between the various logical functions in my logical node are left within the logical node itself and are left to implementation. So this is the lowest, probably the trends towards the lower or even the lowest standardization complexity. Then there's another trend, which I call the matryoshka, from the set of traditional Russian nested wooden dolls. So this is a trend towards nested architectures. A very clear example is the CU-DU split of the 5G base station, or even the higher layer, or even the low layer split, also in the 5G base station. Arguably, this tends to have a higher standardization complexity because you are standardizing not only the logical node itself, but also the sublogical nodes inside this logical node and the internal interface linking them. So of course, you need to specify additional material, additional requirements and interactions. The third trend I have is the Janus Bifrons, from the ancient Roman mythology, god of beginnings, gates, transitions, war and peace, doorways and passages. So Janus Bifrons, if you look at Roman statues, is always figured as a statue with two faces. So then this is a trend towards dual mode or non-standalone architecture. This has probably this is a trend towards the highest standardization complexity. If you think about SA versus NSA, both options, both deployments options of the NG-RAN or 5G architecture, they were both specified at the same time. This was incredibly complex to translate this into logical protocols and architectures. And so this actually required quite a lot of effort on the standardization part, as we know very well. There's a fourth trend. Fourth trend is inertia. Well, inertia is resistance to change. Resistance to change may increase standardization complexity at generation transitions because, well, you have the legacy installed base. And of course, it's fully understandable that operators and also vendors would like to keep as much as possible the track of their installed base. So let's try to see these trends in the various architectures. We'll start with 2G, 3G, 4G, 5G, and also 6G. So 2G GRAN architecture. This is a matryoshka staring at you in the face. The yellow box is actually specified as a nested architecture. The base station subsystem, BSS, was specified as the ensemble of the BSC and the BTS, terminating the interfaces towards a core network. The core network, however, could be a 2G or a 3G core network. So there's your Janus bifronts, there's your interoperability. And this interoperability was added later, was bolted on, once it was realized that this base station also needed to talk to the 3G UTRAN or the 3G RAN architecture. So also inertia came in at this point. 3G architecture, well, believe it or not, 3G architecture was specified as an atom because the RNS, the dotted box, was not specified as a logical node in itself. You had the RNC and the node B, and those interfaces were fully specified. So IUB, IUR, IU interfaces were there from the start. The Janus bifronts, or the interoperability, was there bolted on from the start, was there built in from the start, because this architecture had to cope for packet data as well as circuit switched data. Meaning, yes, it was a very complex architecture. And the inertia, of course, was there because of the legacy capabilities from the 2G networks that also needed to be supported also in the then new 3G architecture. 4G architecture, well, I call it a pure atom because the eNodeB, the 4G base station, was a purely atomic subsystem. All the specifications talked about the eNodeB, and nothing was specified within the eNodeB itself. And of course, this was the result of the initial requirements for 4G. 4G had to support packet data. It had to do one thing, at least at the beginning, and it needed to do it well. Of course, this didn't prevent the evolution of the 4G architecture towards 4G advanced and new use cases. Nonetheless, the foundation was very atomic. 5G NG-RAN architecture shifted the balance towards totally the other way. This was a matryoshka because now we open up the GNodeB. So we have CU-UP, CU-CP, and we have the DU within the GNodeB itself. So we are opening up the matryoshka. But then the 5G architecture needed also to interoperable with the 4G base station. So in the same picture, and by the way, all these pictures are taken from the 3GPP standards, as you see from the references there. So the 5G base station also needed some additional tricks to be able to talk to the 4G base station, hence your Janus bifronts. And all of this resulted from the inertia that there was at that time. Operators were very reluctant to completely discard their existing 4G networks. So we are now facing 6G architecture. So this text is taken from the 6G RAN study item description as approved by TSG RAN in 3GPP just a few weeks ago. So notice I just highlighted the important parts for RAN 2 and RAN 3. So radio interface protocol architecture and procedures for 6G. user plane architecture, protocol design, control plane architecture, access stratum security aspects. Of course, you have radio signaling framework for UV capabilities, aiming at improvements and simplification compared to 5G NR, and of course, in cooperation also with other groups such as RAN 2, RAN 1, RAN 4, data transfer design for various types of data, for example, AI/ML, sensing, and other things. So this is definitely a novelty with respect to 5G. And then radio access network architecture, overall aspects, RAN versus core network functional split, interface, protocol stack, and procedures. Remember what I introduced about the logical architecture. So we're talking about functional split. Which function does that and which logical node is responsible for what? And as a consequence, the logical interface. And of course, also the RAN internal functional split interfaces, protocol stacks, and procedures. So how do we approach this? Well, our approach, at least in my company's view, should be, well, we keep the aspects of 5G that work well. We change when motivated. Remember that the transition from 5G to 6G gives a good opportunity to get rid of the excess baggage or the old baggage that we don't want to keep. And definitely, we add selected functionality for new use cases. And of course, this approach also applies to architecture. So this is what we think is a possible, plausible, and definitely feasible 6G key RAN architecture. Here are some of the key architecture principles. So this should be a standalone architecture only. We would like to keep the added complexity to a minimum. We should try to learn from the legacy or learn from lessons from the 2G, 3G, 4G, and 5G architecture era. There has to be an interface to an evolved 5G core, and we shall include selected open interfaces. So our target should be to minimize complexity and maximize performance. In terms of the trends that we have talked about, that I just discussed, let me just argue a little bit where they are right now. Well, the radio access network is an atom, yes, because we would like to see a standalone and potentially monolithic 6G base station with just a touch of a matryoshka. And the touch of a matryoshka is there right in front of you. We would like to be able to specify a split between two logical nodes within the radio access network base station. One of them, I will call it RAN area function, or RAN for short. And another one, radio unit function, or RUF for short. So RANF and RUF are linked by a logical interface supporting low layer split, LLS. This lower layer split interface, we would like to reuse what is currently specified by the Open RAN Alliance. So this provides you just a sprinkle of matryoshka that should be needed and should be necessary to support basically the flexibility that we believe will be necessary for the new applications. Of course, 3GPP is going to be responsible for the overall architecture and for the all the other open interfaces. So of course, we have the interface between the RAN and the terminal specified by 3GPP. You have obviously the horizontal interface between the RAN nodes, the equivalent to the XN in the 5G RAN architecture. And of course, most importantly, you have the RAN to core network interface between the radio access network and the core network. We would like to keep as much as possible the interoperability, meaning our friend, the Janus bifronts, and the core network. So the core network, in this view, should be a 5G core evolution and evolved 5GC. Of course, that will also take care of the inertia, because we are fully aware that operators have invested greatly in their core networks, so they expect to be able to reuse those core networks for as much as possible. And of course, those core networks will still be able to talk to existing 5G networks. So what is the timeline for this? Well, right now we are in the in between the release 19 and release 20 timeline. Release 20 will start in the August 3GPP working group meetings. So in that time frame, we will start with a new study item for the 6G topic. So after that, we expect to be ready to work on the first normative specifications for 6G in release 21, which I would currently put between 2027 and 2028. So I would say we should expect the first market-ready 6G specifications by the end of 2028. And of course, there's a big asterisk that says indicative timeline, but this is probably a reasonable assumption to be taken at this point. I will just leave you with some ideas for further reading, which will be shared with the speaker notes, so they will be available to you. There's also some material online that should at least provide additional understanding to the thought process behind the standardization of logical architecture in 3GPP. With that, thank you very much, and I hand the connection back to the moderator. Thank you, ladies and gentlemen.
Thank you very much, Gino, for addressing the why behind 6G architecture evolution. As you have emphasized that every generation of a mobile technology is triggered by the need to shed the legacy constraints and support the emerging use cases. While 5G made significant strides in cloud-native design, service-based interfaces, and network slicing, its limitation ranging from deployment complexity to UE diversity make a case for purpose-built 6G architecture, which comprises keep, change, and add approach. Thank you very much. We would now remember the three logical architecture trends, Janus Bifrons, Matryoshka, and Atom or Monolith trend. Thank you very much. We now move forward. Before we move forward, we would request all the participants to please raise your questions in the chat box. Gino, we would also request you to please check any questions raised for you in the chat box, and if you could address them. Thank you. We now move forward with the keynote 2, the new edge for 6G, which will be delivered by Professor Daniel Kilper. So Professor Daniel Kilper is the director of the Connect Center and professor of Future Communication Networks in the School of Engineering in Trinity College, Dublin. He has made pioneering contributions in communication devices and systems research, primarily spanning 3 areas: energy-efficient communication networks, optimal performance monitoring, and AI and software-defined networks. He is a senior member of IEEE and chairs the Optics Working Group in the IEEE International Network Generations Roadmap. Over to you, Professor. Thank you.
Hi, thanks, Sonali. Let me share my screen here. Just 1 minute. Okay, so I'd like to thank the organizers at TSDSI for inviting me here today to talk with you at this Tech Deep Dive. I'm really delighted to be here. And I'm going to talk about actually edge networks and a new and evolving edge network for 6G and how that plays into the 6G architecture that we just heard a lot about in the last presentation. So, and to start with, I want to acknowledge that there's several key changes and trends that are happening that are shaping networks today. And one is this AI revolution that we're all right in the middle of. There's a lot of questions, as we've heard brought up already today, about will 6G go AI native? How are we going to use these new AI tools within networks? There's also a lot of activity around sensing and communication. Now, sensing has been around in radio and optical for a long time, but we're seeing them integrated more closely within the communication systems and using the communication system as a distributed sensor or sensing tool to bring more value, as well as to make networks more resilient. Now, the other major trend is this kind of access metro edge convergence, that we have the compute continuum from IoT to edge to core that's going on. And I'm going to focus a lot on that, but also how this metro edge convergence is connected to this, what's going on in AI and the sensing and communication trend. So I'm going to start with by just saying that it's my firm belief that AI is the next killer app for networks. When you talk about the network, this is what's going to drive growth in the network for the foreseeable future. It's similar to what happened with video, all the Netflix and YouTube videos and so forth, really driving capacity and functionality and use of the network. Well, I think AI is going to be doing that, and we're seeing trends already that are moving in this direction. There's a very nice white paper out by Cisco talking about AI infrastructure for the agentic era. So they point out that with generative AI, we moved from single modal data to multimodal data, generative AI, and that's going to evolve into what we call agentic AI. So these are AI agents. Generally, they're deployed at the edge for supporting certain specific functions. They involve a lot of training at the edge and using that compute continuum. You can see here in the figure that they're going to make use of these edge AI data centers in a huge way, and so that's really going to drive a lot of the traffic and need for new functions and capabilities in the radio access networks and in the metro edge in general. In fact, you can see, for example, Zayo is scaling out their metro network fibers. A lot of this is happening now in the core of the network, and it's going to be moving towards the edge. And so like with light counting, they're talking about with optical interfaces. We haven't seen an exponential steep growth in capacity like shown in the upper right-hand corner here in many years. And so this is really going to be driving a lot of what's happening. And that's initially in data centers, but it's going to move more and more to the edge and make more and more access of the RAN networks that we're going to need functionality there. Now, I want to point out that networks have largely been constructed in this hierarchical way where you have your access networks, your RAN, your PONs, and your microwave backhaul connecting into distribution and metro core network, and then a long haul network. And so it's kind of this tiered hierarchical network with clean separations between each of these different hierarchies within this metro region. And gradually we've been building out this mesh network in the metro core. And what we're seeing now is that this has changed. It's evolving into, instead of an internet backbone, to an AI backbone, where we have these data centers that are supplying that AI functionality, doing all the training and building up the models. And those are connected by what we call the data center interconnect network, or DCI network, massive point-to-point connectivity between data centers, both regionally and across country. And then we have edge clouds within the metro areas, where we have edge data centers, micro data centers in your access nodes, your multi-access compute capability supporting your centralized RAN functionality as well. And these AI clouds ultimately are going to, or these edge clouds are ultimately going to become AI clouds, right? And AI functionality there at the edge. And so I want to talk about that a little bit. So we need to push capacity into the metro edge. This is one of the things that we'll need in the 6G era. And then we also need to move capacity efficiently around those metro networks, and then also serve this growing range of diverse applications there, especially AI applications. I just want to give one quick example. There's a lot of interest in kind of flash events, high capacity, low latency events, but in particular, looking ahead towards using AI to respond. And so here's an example. So you have a traffic jam. Instead of just kind of Waymo reporting of, okay, there's a traffic jam and the user has to figure out what to do about it, we're talking about pulling in sensing data, video, CSI information from the network, and then controlling the traffic signals, controlling autonomous vehicles, actually taking action to help relieve this congestion. And for that, we take advantage of AI tools embedded within the network, and we need to move our resources about the network. We need to turn down resources that aren't being used here and send capacity and compute and data over to where the AI is, and supporting this low latency, high capacity response feedback loop, taking advantage of that AI. So these are the types of scenarios. It could be emergency response, disaster response, as well as these kind of flash crowds and other type of congestion events that we'd be working to provide capability for. Now, what sort of network do you need in order to do that? So it's one thing is we need AI within the network, and we need network functionality. So let me talk a little bit about that. And first off, you could argue that, well, I can do that today just by building out massive capacity and deploying massive compute resources everywhere. Well, that's not going to work because AI requires an enormous amount of energy. We're seeing that Google's energy use is climbing. I'm just using the example of Google here, but there's many others. This is true across the industry. People are looking at mini nuclear reactors in order to provide this. So we can't just deploy and keep deploying and make use of massive capacity. We need to make systems that are adaptive and can make best use of renewable energy and be the most efficient that we can. And for this, we want to take advantage of our architectural capabilities in the network. And so I'd point to the O-RAN architecture. We heard from the last speaker that 6G is going to borrow elements of what's happening in these open radio architectures. And I fully agree with the previous speaker. I think from a kind of 5G RAN point of view, we're going to see much of the same happening, but evolving in important ways, and in particular, supporting these open functions and RAN capabilities. Now, importantly, this architecture allows for both near real-time and non-real-time hierarchical controls within the network, and we can take advantage of these in deploying our AI applications to control the network as well as to support AI in the edge. Now, what we believe is needed here is the deployment of various AI tools within the network. So AI control elements, model and data management tools, and these can be deployed within, they could be X apps or R apps or embedded functions within the architecture itself that might show up in a non-real-time or near real-time RIC. But also, importantly, they need to find a home in the network OSs and transport SDN that's going to be part of the transport network that's connecting these radio resources. And by putting tools into the network this way, we can then separate out the AI service management and orchestration as an over-the-top function, where we're seeing many different developments there, and there'll be a wide marketplace of capabilities there. But we need these various tools within the network to help support in an agnostic way the various AI services that might come over the top. Now, so the idea is that we embed these AI controls throughout the network to help provide this advanced functionality. These AI controls need to talk to each other to help coordinate the various functions and provide that AI network control. But at the same time, we need tools and knobs that these AI controllers can adjust in order to support these advanced applications. And that's where we see some changes coming in terms of the physical layer for 6G down the road. And in another project that we have funded through Horizon Europe, EcoENet, we're looking at the development of mesh networks all the way to the edge. So not just in the metro where we're already developing mesh networks, but really pushing to the edge. And at the edge, you can't supply everything with fiber. You need fixed wireless, and we need it at high capacity to support these advanced applications. So we're talking about bringing in sub-terahertz fixed wireless, high capacity millimeter wave interfaces that needs to work seamlessly with your wired fiber network to connect your in-network decentralized AI together with your split PHY processing and your radio processing and your AI applications, right? So, and in fact, there's a new approach to radio that's developing called cell-free distributed MIMO. And moving to cell-free architectures, we need a more adaptive network to support that. And I'll talk a little bit more about this. So there's functionalities here where I can basically allow for direct wireless connections across this mesh, but I can also use route diversity and move other paths through the network. And in particular, I'm interested, can we do combinations of radio and fiber backhaul or call it front haul or X haul through the network? And so this would be an important new capability. Now, to support this, we view that we need to move from what we've been talking about for 20 years, which is convergence of radio and optical systems, to what we're terming a confluent network. So with confluent networks, we need to fully bring together the radio and optical pieces of the network, as showing in the AI case. So we need AI controllers that work across each of these technologies to provide end-to-end AI, but we also need that in terms of how the systems operate. And so with confluent systems, they can natively support multiple transmission media and their signals, as opposed to just having kind of side-by-side systems that are handing off signals. And in this way, you can have multiple parallel paths all working in conjunction with each other, and path diversity all the way out to the edge of the network. That gets you the capacity and latency that you need for future AI applications. And this isn't going to happen tomorrow. It doesn't happen overnight. It's going to be an evolution, I'd say, across the whole 6G period as we start to deploy more of this. Now, the technology is there. There's been quite a bit of results in recent years looking at analog and digital radio signals in fiber, and those are highly compatible. And we understand how to make them work together, as shown in the upper right-hand corner there, with analog radio signals together with 100 gigabit QPSK digital signal. We've looked at the combination of putting sensing signals, so analog sensing signals such as distributed acoustic sensing, in with both analog and digital as well. There's some other results that we have here on that, and shows good compatibility where you need to operate these systems. So that all looks great. And so we can think about in the future a network node that is basically taking advantage of sub-terahertz fixed wireless, as well as free space optics is coming down the road. And then we have our traditional fiber wavelength networking that can also provide optical spectrum services to support sensing tools within the network. And we're looking at a terabit per second over a kilometer for sub-terahertz, and a terabit per second over a kilometer for fixed our free space optics. And actually, free space optics pretty much has that already. It's a question of making it more affordable and scalable, whereas the plasmonic sub-terahertz is something that's new and emerging, and has a lot of promise in that space, and we think it's going to be able to hit those targets as well. So that's an exciting development. Now, with these capabilities, if we're able to create these mesh networks all the way to the edge, it means that we have adaptive, dense mesh networks to support the densification of radio nodes, to support a cell-free wireless environment. So we can go from these fixed cells to a more adaptive cell-free environment where you can basically bring together and cooperatively operate the different access points in order to best serve whatever your user needs or the application needs that you're connecting to the network over. And that's an important capability for 6G. So we're looking at an evolution towards a mesh multi-technology edge for 6G, so enhancing connectivity for AI compute and edge data centers. This will increase the bisection bandwidth between edge data centers for advanced and agentic AI, which we'll need. And then connecting users and IoT to AI applications in the edge cloud with lower latency, high capacity, and greater resilience through route diversity. This will support scalable, cell-free, distributed MIMO architectures, integrated sensing and communications over the same network. And I didn't get to go into it here, but we need to be adaptive for sustainability so that we can run these networks off of the renewable energy smart grids, which are very demanding and variable in their energy supply. And so we need a network that's going to match that for future sustainability. So that's our view of 6G going forward. Thanks for your attention, and I'd like to recognize support from Horizon Europe through their 6G SNS program, EcoENet, and 6G Excel projects that I've described a little bit for you here today. Please check on the websites to learn more about each of those. And you're welcome to also visit our Connect Center online, and happy to talk with you more about that. Thank you.
Thank you, Professor Dan. Thank you for introducing thought-provoking ideas around AI-driven edge compute, decentralized orchestration, and multi-technology edge networks, all of which addresses the challenge for the traditional hierarchical telco model. Your call for the confluent systems supporting analog, digital, and sensing signal natively highlights the need to integrate AI, sensing, and communication seamlessly within the fabric of the network. We would also like to thank you for highlighting the need for the trade-off between the sustainability and increasing demand for AI applications. Much appreciated. Thank you, sir.
Okay, thank you.
With this, we now move forward for the final keynote for the first segment of today's session, which will be delivered by Mr. Balazs Bartney. Mr. Balazs joined Nokia in 1998 and started to work on circuit switched mobile switching. In 1999, he joined the research group on IMS and soon started to work in 3GPP standardization on IMS architecture. He was the chairman of 3GPP TSD RAN from 2017 to 2021. After finishing his chairmanship duties in 3GPP in 2021, he has taken the pre-standards and ecosystem lead for Nokia on 6G and has been actively engaged in related activities since. The title of the keynote 3 would be Architecting 6G, Research to Standards, Emerging Views. Over to you, Mr. Balazs. Thank you.
Thank you very much. And thank you very much, Sonali. Thank you very much, DSI friends, for having me. It's a great honor to speak to you today. And we have heard some very good insights from Gino and Daniel already. Let me try to complement that with some further sort of technology and architectural trends for you today. So we have heard a great historical recap from Gino and some very good insight from Daniel on which way some of the transmission and radio technologies are heading. Before I go into some of the more technical details, let me try to give you a few thoughts on what the fundamental drivers are. So, okay, I need to move this forward. Here we go. Okay, so focusing on the drivers first. So the way I think about drivers is there are always drivers coming from a business side, so from a commercial side, and then there are always drivers coming from the society, from humanity. So if we look at what the drivers are from a business perspective, not only for 6G, but sort of for communication technology in general, one of the key business drivers that we see is TCO reduction. So using the capabilities of AI, of cloud platforms, some of the technologies that also Daniel mentioned, to go into sort of extreme reduction of TCO, intent-based automation, and also cost-efficient migration towards 6G from the existing networks are certainly a big part of this. Performance and resiliency. I mean, there's no two ways around it. To make the next generation of communication network successful, it has to provide a leap in performance, and it has to provide a leap in resiliency. As we have moved forward from 2G to 3G to 4G to 5G and now to 6G, as Gino also showed, we have seen that the cellular networks have taken a even bigger role with every generation in terms of the critical operation of our network. So resiliency is becoming extremely important, and there are also standards elements to that, as I'll allude to a little bit later. But a big part of resiliency also comes from product implementation. And last but not least, you got to make money. I mean, there's no two ways around it. Cellular is a business, so there needs to be a better fostering of monetization. And if we want to be honest, I think this is where sort of 5G is still a bit lagging behind expectations. There's a good chance it will still get there, but it is certainly, in my mind, lagging behind our expectations, what we have foreseen for 2025. And then for 6G, with even sort of better programmable networks, unified API framework, and similar technologies, we have a much better platform to actually monetize the cellular network assets. So that's sort of the business perspective. If we look at more the human or the societal perspective, environmental sustainability is clearly a #1 goal. And we have seen the challenges that also Daniel outlined with the power hunger of AI. So this is clearly, in my mind, the biggest challenge of technology over the next decade is how can we actually make the AI-driven digital infrastructure actually sustainable, not only from an energy perspective, but sort of raw material reuse, etc. So cellular needs to take a big responsibility for that. And with that, 6G really needs to be showing a leap in terms of energy efficiency and sustainability. Security, privacy, and trust. We have had this as a central part of a cellular design, but now with the need for quantum safe system, trustworthiness of AI, and sort of highly automated identity management, this will have to be taken to the next level with 6G. And last but not least, and this is where I believe India is especially sort of in a key role, is digital inclusion, ubiquitous connectivity via terrestrial and non-terrestrial access, connectivity at a reduced cost, sort of extreme coverage going into areas that previous generations could not economically go into. And for me, this is where the rest of the world very much counts on India and innovations coming out of India, so that we can solve this challenge with 6G. So that's sort of the drivers. And then if I look at the technology enablers, and then at the end of the day, we need to basically match up the drivers and the technology enablers towards an architecture and a technology that then comes together and fulfills those requirements. And if I look at the architecture first, and I try to bring a slightly different perspective compared to what Gino and Daniel presented, basically amending that a little bit. What I put here is some of the key elements that we see driving the architecture design. And for me, number one is it needs to be a much simpler, more streamlined architecture based on the standalone paradigm. We know that with 5G, we've done by now, I think it's clearly a mistake of having both a non-standalone and a standalone track. And with 6G, we simply cannot afford that dual track approach. So we need to have 6G based on a standalone paradigm from the get-go. Modularized design of the architecture, I believe, is key as we're moving towards the next generation of devices. And the last 10, 15 years has clearly been dominated by smartphones. The device ecosystem has been quite monolithic in a sense that all our devices were very similar to each other. But moving forward, to me at least, it's clear that we're going to have a much more versatile kind of devices. So we need a more modular architecture to better cater for this more versatile device ecosystem going forward in a native and efficient way. End-to-end resiliency, as I alluded to that earlier, as our cellular infrastructure is becoming more and more critical, part of the sort of the national critical infrastructures, not just with IoT, but also some of the public safety usages of our networks, first responders, etc. It's very clear that we have to take the network resiliency to the next level with 6G. And last but not least, I think new service requirements. I mean, one thing for me is reasonably clear that at this early stage of 6G development, we can have sort of assumptions on what the new services will be. And I think what Daniel said about AI is very true, that AI is definitely going to be one of the drivers for the next generation of services that cellular networks have to cater for. But if we look at the last few generations, we really didn't know for sure at this early in the process what the services are going to be that will make the next generation successful. So basically, we have to design the system and the architecture in a way that is sort of easily adoptable and easily extendable towards services that today we just don't simply even see. Then if I look at move away from performance and move towards more sort of scalability, operations, and optimization, sustainability by design is going to be critical, not just for a radio. I mean, as we know today, if we look at a cellular network, the energy usage, the vast majority of the energy usage actually happens on the radio side. But more and more, especially with AI, we will see energy usage growth also on the core network side, and that's simply not sustainable. So we need to have technologies that keep the energy usage in check and allow for maximum reuse of materials and equipment. In terms of moving towards a more programmable network, I think unified exposure is key. AI native architecture is absolutely key. I mean, these are almost given. They're not even sort of cellular specific trends. I would consider these as more generic trends in the digital infrastructure. And security the same way. It's something that the cellular network also has to follow some of the other digital industries in terms of making sure that our networks are quantum safe and secure. So that was sort of the overview of the architecture technology trends. And if I move a little bit into radio, just to give you some ideas on what's happening on radio. With every new generation, the assumption is that there's going to be a new non-backwards compatible radio design. There are several reasons for that. New spectrum, basically the once in a 10-year opportunity to actually have a chipset or device refresh. And we are going to see the same thing here. So we will see a new non-backwards compatible radio for 6G. And first and foremost, it's the performance that has to basically show a large step compared to 5G. Very high data rates, coverage is critical. And also, if I think about data rates, there has been this unfortunate trend that peak things get sort of marketed with peak data rates. But when you look at user experience, that's really not what matters. What matters is you get reasonable data rates everywhere, and reasonable data rates is 5 to 10 megabytes. So if megabits per second. So if I get that data rate almost sort of ubiquitously everywhere, that's going to be a true leap in user experience when it comes to cellular networks. And always the coverage bottleneck is uplink. So we have to, or we will introduce technologies that enhances the uplink coverage, and not just by higher power classes, but also other technologies. And if I look at sort of deployment realities, we know that in most parts of the world, the grid is pretty much fixed. So getting new sites, getting new, expanding the side grid is very difficult for a multitude of reasons. So we basically have to work with the existing side grid. So 6G will have to be exhibiting all those enhanced performance capabilities, better coverage, etc., using the existing side grid. So we can't really base our assumptions because of commercial realities. We would all like to have more sites. I think that's, especially coming from a network vendor, I would love to see that. But the commercial realities are just not that in most parts of the world. So maybe moving away from then the architecture and the radio a little bit, migration, and this is one element that I specifically wanted to explain today, because it's a very critical part of making a new generation successful. You can have all the great sort of design, both on the radio side, core network side, architecture side for a new G, but if there is no viable migration path from existing networks towards these new networks, it's always going to be an academic generation. So it's very clear that having a commercially viable migration path towards 6G is one of the decisive elements of making it a commercial success. And what we see here from a Nokia side, as I explained, is 6G is standalone. 6G has to be standalone. We can't go and veer off certain different side paths along the non-standalone paradigm. So then how do we actually get to that single standalone system? And for us, the key element is having an efficient spectrum sharing. So there needs to be a mechanism that allows sharing of spectrum from 5G or between 5G and 6G in a way that we keep the efficiency and the high performance. We all know we had dynamic spectrum sharing between 4G and 5G, but that was not, it was basically technologically a failure in a sense because of the different radio designs of 4G and 5G. We lost about 30% of performance. So now when we go into 6G design, one of the key design elements of 6G radio has to be the assurance of an efficient spectrum sharing with 5G. And this is, for us, this is very much possible. And the cornerstone of that is 6G radio, we assume, would be built on on a 5G NR compatible waveform and design. There is so much we can still do in terms of performance leap with the existing waveform paradigm, and then having that paradigm also apply in 6G will really allow for operators to have a cost efficient and commercially viable migration. And if I sort of couple up multi-radio spectrum sharing, so 5G, 6G spectrum sharing with carrier aggregation, you actually get the best of both worlds. You get the coverage, and then you also get the bit rates from day one. So then moving on a little bit, let me just show you a bit of the timeline. I think Gino very nicely outlined how we've basically built the cellular ecosystem across different generations across the last couple of decades. And what I want to zoom into here is how we're actually building 6G itself. So here you can actually see the detailed timeline of how we see the 6G standards developing, in particular in 3GPP, or in the context of actually a 3GPP ITU interplay. So the top green part is basically showing the ITU timeline with some of the key milestones there. So the WRC 23 and 27 are essentially important for unlocking new spectrum for the industry, and then the requirements work, and then the work on calling for proposals from ITU is then important from the perspective of actual technology standards. So the way this comes together is 3GPP will submit its eventual 6G design towards ITU as a proposal for IMT 2030 or 6G, and then there will be an evaluation process in ITU, and at the end of that there will be a acceptance of proposals, and that will then constitute the IMT 2030 standards in an ITU nomenclature. Then when it comes to 3GPP, so 3GPP then actually does the technical standards, and we have already very much started the work. So we started the requirements work, both on the system side and also on the radio side. And we have actually just in the recent plenary a couple of weeks ago approved the studies for the working group, so the detailed technology studies, and Gino has shown you the scope of that work when it comes to architecture and protocols. And that work will now start in August, first with the physical layer, and then in October with protocols and architecture. And it will span about 18 months. So the study will take about 18 months. After that, we will do normative specification work in release 21. And in our estimation, the specification work will conclude around the very end of 2028, maybe the beginning of 2029, where we freeze the specs, freeze all the necessary protocol elements. And then what does that mean in terms of deployments? We actually see that we might have the initial commercial deployments already towards the very end of 2029. Most likely, most of the initial deployments more in the early 2030 timeframe. So that's sort of the timeline that we can count with. Of course, this is very preliminary, so especially the back end of this timeline hasn't yet been formally decided. But at least from our side, we see this as a realistic timeline going forward. So that was what I had today, and thanks again for my TSDSI friends, Sonali, and also for all of you for paying attention to my presentation. Hopefully it brought some interesting insights, and if you have any questions, I'll be here on chat. So thank you very much.
Thank you, Balazs. Thank you for offering a crisp blueprint for a simplified, modular, and service-optimized 6G architecture, which emphasized on AI/ML native design, zero-touch automation, programmable APIs, and security by design. We align with you that these aren't optional capabilities anymore. They are the foundational pillars needed to support the ubiquitous and intelligent connectivity. We also thank you for also highlighting the honest perspective on the business aspects of monetization and the need for the cost-effective migration to 6G. Thank you for also highlighting the timeline for the 3GPP and ITU and 6G IMT 2030 framework. Thank you very much.
Thank you very much.
Thank you, Max. We now move to the second segment of the today's session, which is the panel discussion on new network architecture possibilities for 6G. The panel discussion will be moderated by Mr. Pranav Jha. Over to you, Pranav. Thank you.
Yeah, thank you very much, Sonali. I hope I am audible. Good afternoon, everyone. So I welcome you all to this panel discussion on the topic of new network architecture possibilities for 6G. We have five esteemed guests here, and let me first introduce them to you. Can we go? Yeah. So our first panelist is Dr. Parag Agrawal. He is a principal project associate at IIIT Delhi, specializing in 5G and 6G wireless communication systems. He received his PhD from IIIT Delhi in 2019 with research focusing on MIMO OFDM transceivers under hardware impairments. From 21 to 24, he worked at HFCL Limited as a 5G system architect, leading the development of advanced open radio unit architectures and RF optimization techniques. His interests include baseband processing, RF hardware impairments, software-defined radios, and AI/ML in physical layer. He has authored several IEEE publications and holds patents in wireless communication systems. So our next esteemed panelist is Mr. Rajat Agarwal. He's currently the Principal Solution Lead, Network Services Emerging Technology at Tech Mahindra. He's a passionate telco professional with 18 plus years of experience, having diverse skills and proven experience in product management and pre-sales of 4G, 5G, RAN, ORAN, radio products and services, AI network platforms, and network evolution consulting areas. So welcome, Mr. Agarwal. We have already met Gino Massini. He's the principal researcher with Ericsson in Sweden, and we are very happy to have him as the panelist also. Yeah, so can we go over to the next? Yeah. So our next esteemed panelist is Professor Abhay Kumar Sai. He currently serves as an associate professor in the Department of Electronics and Communication Engineering at IIT Roorkee. His research interests focus on realizing cell-free massive MIMO systems for next-generation wireless networks and exploring the applications of deep learning in wireless communication systems. Following his PhD at IIT Kanpur, he had joined Samsung R&D Institute as a senior lead engineer, where he played a key role in developing 3GPP release 14 features. Yeah, and our last esteemed panelist is Mr. Subhash Mandal. He leads the R&D efforts for 5G product development at HFCL as a senior vice president. In this role, he works with academia, standards development organizations, open source, and technology partners. The portfolio includes standards and research in 5G and 6G. Product portfolio includes ORAN-based macro RU, indoor small cell, medium-range outdoor small cell, and transport products for interconnecting disaggregated RAN nodes. Welcome, Subhash. So I welcome all esteemed panelists, and I know here is a short plan for the panel discussion. I would like to invite all the panelists initially to share their introductory remarks, and then once they have shared the remarks, then we will go over the question and answer session. So let me first invite Dr. Parag Agrawal to share his thoughts. Parag, over to you, please.
Yeah. Thanks, Pranav, for having me. Thanks, TSG site, for having me on this panel. So, Pranav, the topic that we are discussing is standardizing the 6G and talking about the 6G and all. And of course, that we have seen that in the 5G, that 5G is evolved totally from the earlier generation, 3G and 4G. In both architecture, network architecture, core architecture, or from the RAN side. And the reason is that the demand of a different type of use cases, the high rate and all. And similarly, when we are looking at the 6G, 6G also have a different use cases, enhanced use cases as compared to the 5G. And it's had their own use cases like a terahertz communication, integrated sensing and communication, AI native. So all these also lead us that 6G required a different RAN architecture or an enhanced RAN architecture from the 5G. And of course, from the core point of view, as the earlier respected speakers mentioned, that it should be the evolved service-based architecture as compared to the 5G. I'm totally agree with them. But I just mentioned a couple of more points about this, that we should not we should also consider the 2G, 3G bands as well, because see, moving towards to the new generations, we are looking to the new spectrums and all. But as we see that nobody is talking about the 2G and 3G, and their spectrums are minorly reusing in the 4G and 5G. Why don't we have included totally into the 6G, and we can explore them for the new use cases or the different use cases like IoTs. Instead of putting all the IoTs on the higher bands, we can use the 2G or 3G bands as well. Or another way to looking at the 2G, 3G band that we can use for the uplink, where we require a less peak data as compared to the downlink. In some of the cases, so these kind of things we can also include it in the 6G research as well. So these are my takes, and of course the AI, the sustainability. Of course, sustainability is a very essential for the 6G, because all the devices that we have seen in the 3G, 4G, 5G, though all are the power hungry, and the carbon footprint is too high. To support that green initiative of the UN, the sustainability goals and all, we should also look towards the sustainable communication. From the core architecture as well as from the RAN architecture. So that's it. Thanks.
Thank you very much, Parag, for sharing your thoughts. Next, I would like to invite Rajat to share his initial remarks. Rajat, over to you, please.
Hey, thanks, Pranav, and been honored to be part of this STEAM panelist discussion. So I think we have already been heard about some powerful and forward-looking thoughts on how the 6G architecture will evolve from modularity to openness and cloud-native design and the service-based architecture. And what we have learned with the deployment of 5G, what had worked in the 5G networks. Now, when we look into 6G, I would like to bring on the spotlight onto 3 core enablers which will be fundamentally redefine the role of the network itself in the 6G era and have the impact on the 6G architecture. And these enablers are how we will bring the AI natively intelligent fabric into the network, the integrated sensing, and the convergence of the terrestrial network and the non-terrestrial network. And these enablers are not going to be an add-on functionality or features to the network. It's going to be a natively part of the 6G network. So when it comes to the AI native intelligence in 6G, the intelligence, we see that it's going to be the natively embedded and making a network autonomous. We are talking about an architecture where the AI agents operate across the different domains like RAN, core, edge, and making a real-time decisions, automating the network operations, understanding the user or application intent, and dynamically personalizing the service delivery. The AI impact is not just limited to the control the functions. This can maybe further extended to fundamentally change how we design the network protocols or the network functions itself. What we believe that with AI, we probably can look forward into break down the network functions into more modular and app-like sub-functions, which can be assembled or optimized on the fly based on the context, use case, or environment. I just give you an example that we have a network functions running in today's network, be it a mobility use case, be it a IoT use case, it's the same network functions. But when we move into a 6G era, we probably can have a modular sub-app functions which can be aligned based on the use case, whether it's a mobile app application or IoT applications. So that's the way we look at it, that AI native intelligence will be embedded and will bring more modular application or some functions in the network. The second enabler is a sensing related. if we look at it, the traditional communication networks had been sending the bits and been blind towards, how the data will be, what is the environment and what is the vicinity of that recipient, whether it's a user, mobile, or whatsoever. In 6G, what we see that it has been evolving towards a perceptive networks. One can not only transport the information, but it can also sense the understanding the physical environment, and that will be fundamentally change how we will build the network and perceive the network. And the third, what I would like to touch upon, the integration of the terrestrial network and non-terrestrial network. The LEO satellites, the HAPS, the UAVs must be natively integrated in the terrestrial network infrastructure to provide the coverage, be it in rural or be it in outside of the urban area. This architecture convergence will requires a unified routing, real-time orchestration across the ground and the space network, and helps to cover the coverage gaps, natural disaster, infrastructure outage, and brings the resilience to the network. So to make, in summary, to make the 6G a truly transformating and not just evolutionary, we must architect the networks more intelligent, perceptive, and omnipresent. And these three core pillars, what we believe is going to be a new foundation of the 6G network that helps the network to think, see, and reach everyone and everywhere. Thanks.
Thank you, Rajat. Thank you very much for highlighting some of the real important points that we must look at and how they will impact the architecture for the 6G system. Next, I would like to invite Professor Abhay to share his thoughts. Abhay, over to you, please.
Hello. Good afternoon, everyone. Thank you, Pranav and Sonali, for inviting me for this discussion. So it is a pleasure to be a part of this discussion on new network architecture possibilities for 6G. As we look ahead for the next generation wireless technology, it's pretty clear from the previous discussion that 6G is not only about just being faster, adding additional bandwidth, or bringing new use cases. It's also about reimagining how networks are designed, deployed, and operated, maintaining the sustainability and environmental aspects, and also bringing values to the business prospects. Now, I'll be briefly talking about three major points around the cell-free architecture, and that probably will be part of the networks. One of obviously is this AI native support. Now, definitely the few areas where AI can play a crucial role that are related to resource management, maintenance of the networks, and the real-time optimization. But these are the three early phases of AI network which I expect to be part of the architecture. There are like it can be also included in the physical layer, solving many sub problems which can also be dealt through the AI networks. The another central aspect which requires a radical change, which already being pointed out by in the previous talks, that is cell-free massive MIMO. I will give you a basic idea what is cell-free massive MIMO. So it's basically de-integrating the RAN, which is basically a G node B, which is located centrally, into multiple sub access points, or you can sub base station, which is called as an access point. Now these access points are connected through some centralized server, bringing the aspect of the cloud networks, or you can say virtualization of the networks. And then these access points serve the users through multiple directions, bringing advantage of spatial multiplexing as well as diversity, which can give you very good gains in terms of spectral efficiency as well as energy efficiency, which also is a crucial aspect of designing any network. And obviously, the vision of selfie massive network architectures are very much aligned with the ORAN, the openness in the radio access network, which basically brings like you have to standardize different parts of these components, APs, and the CPUs or the core network, so that there will be a seamless connectivity along these different nodes. Obviously, these architectures or also very much integrated for maybe the RIS, suitable for integrated sensing and communication, and as well as terahertz communication, exploring the higher frequency bands. And obviously, this requires a lot of study, and there are a lot of challenges also involved into it, and there are there are a lot of works is being happening around the world. Lastly, before we conclude, we must talk about non-terrestrial network. That includes basically satellite, high altitude platforms, and the UAVs, and that are also becoming an integral part of the 6G vision. And we need to talk about how this cell-free architecture or the existing RAN architecture can be seamlessly integrated with the non-terrestrial network, giving a better coverage, better connectivity to the users. Okay, so lastly, I would like to submit my thoughts to the panel and look forward to the discussions ahead. Thank you everyone.
Thank you very much, Abhay, for pointing out some of the very key aspects, like new things like cell-free, massive MIMO, and and the impact of that on. Next, I would like to invite Subhash to share his thoughts with us. Yeah, Subhash, over to you, please.
Yeah, thank you, Pranav. And thank you, TSDSI, for having me here on this esteemed platform with the global experts here. It's true privilege. So, Pranav, I will start my opening remarks with just 6 bullets for 6G. My first bullet would be a borrowed bullet from what Gino just presented in the keynote. Leave the baggage, usher the new. Whatever did not really work well, does not make sense to take forward from 5G NSA as an example, drop it and then move forward with the new thinking. The second point kind of borrowed from Blase's presentation, keep the hype low, focus on value addition. How do you bring total cost of ownership, monetization? How do you really reduce the energy cost? That would be my second point. Then moving to the third point, I would say that rise beyond the speed race. So generations have evolved from high speed, high speed, high speed. In my view, we have come to a stage where the speed is good enough to cater to most of the applications. Of course, there could be areas where getting into terabit per second would make sense, of course, with the immersive communications coming in. But rise beyond the speed and bring the value. How do you leverage that speed in terms of providing capacity in a ubiquitous manner? That would be my third point. My fourth point would be that treat AI with utility focus. So while there is a lot of hype, which we have seen in 5G also, network slicing as an example, was a lot of hype around that. How much of that has brought in utility? Of course, I am not questioning that, but that is something that can be looked at. So similarly, AI is bringing in a lot of hype. Let us treat it with the right utility focus. There already has been discussions. Blase talked about the impact of the AI on the energy efficiency. Gino also talked about it. And an addendum to this in this point is that intelligence at the right place in the right proportion. So if you look at 5G, the service management or orchestration has been an area where the intelligence has been looked into. Autonomic network has been investigated quite extensively. Automating a lot of those aspects has come in. Now, what is the level of intelligence and autonomy that we can really manage the network with without creating an immunodeficiency syndrome in the network, right? That is an essential question for us to ask. There are a lot of discussion happening on the introduction of AI in the RAN. What functions can really take that function? Is it the beamforming, beam optimization? Is it the channel estimation? Is it the modulation, demodulation? I think there are things to look at. So treat AI with the caution, with application in the right place, in the right proportion. My fifth point would be stay grounded. but keep the horizon open. So while there has been discussions that what waveform shall we use, OFDM or move into something outside OFDM. While OFDM has challenges, it has its virtues as well. But then should we be limiting ourselves with that? That's an open question. I don't think I have an answer to that. My last point would be that the new capabilities that ITU has proposed in terms of ISAC, integrated communication and AI, ubiquitous connectivity, how do you bring utility around them? So this would be the 6 points I would like to focus on.
So thank you very much, Subhash. As always, it was very illuminating hearing you. Okay, so I will now go to Gino. So Gino, would you like to share some thoughts? You've already, made a presentation. So.
Sure. Thank you very much. And first of all, thank you for moderating this, and thanks everybody here for being here, and thanks for having me to the organizers. Just a couple of things I would like to share. So basically on two topics that I follow very closely, and you might say are dear to my heart. One of them is NTN, and another one is sensing, or in the 3GPP jargon, it's called ISAC, integrated sensing and communication. So NTN is about, I would say, two communities coming together: the terrestrial community and the satellite community. I've seen this in my previous role as 3GPP Round 3 chairman, and you had people and companies coming into the room with totally different ways of discussing and arguing, totally different company cultures. So in order to make technical progress and in order to avail yourselves of the advantage of the open discussion in 3GPP, you need to start speaking the same language. First time this happened, it was a bit of a harsh approach, because they came, the NTN people came to the terrestrial table. It must have been around release 14 or 15. And I remember there were some delegates that said basically, no, you guys should just simply go away, because we don't like you. You're simply going to start stealing our spectrum. You want to steal your lunch. This is no place for you. And rather than fighting back, the NTN people were very patient, and they said, no, but you know what, we see the advantage of ecosystem standardization. We would like to be competing for a larger piece of the pie, where the pie itself actually becomes bigger, and so on. So it takes perseverance, it takes effort, and before you know it, we had the first normative specifications, including NTN, in release 17. First study item release 16, and I mean the whole discussion came a long way, actually. And so this was it took perseverance. The drawback of the length of time is, well, there's a lot of hype. And these days, if you come to 3GPP working group meetings, you will see that anybody and everybody wants to be seen discussing NTN. So sometimes I would have to ask the provocative questions. So you are a UE vendor, or a UE chipset vendor, or a very specific provider of a very specific ecosystem. And I hear you would like to teach NTN companies, big satellite manufacturers, exactly how a satellite is supposed to work. Exactly how many satellites did you launch lately? And it would be the same thing if I, that work for an infrastructure manufacturer, was trying to teach some UE vendor how the UE should behave in this or that way, or you guys should implement the UE in this and that way. So going to 6G, the ecosystem will shift into wide discussion mode once again. So lots of open discussion, lots of hype, lots of companies, and lots of fresh new delegates with brand new ideas, and sometimes it takes a bit of effort to synchronize everybody. NTN, I think, is a good paradigm of that, because if the effort is honest enough, and if you have good attitudes on both ends, you really have marvelous results. Also in terms of architecture, which is my, you know, the love of my life, RAN architecture. By now, you might understand. And release 17 was a milestone in NTN architecture because we have started to work with this. Release 19 was another milestone because we said, okay, we're going to launch a GNode B. So the base station is on the satellite. And again, it took a lot of effort to bring everybody together on that side. This doesn't mean that, of course, we limit ourselves to a certain thing, because one of the things that this will enable also going to 6G is what some companies have referred to as data centers in the sky. Because once you have the base station in the satellite, of course, well, it's a bit of a stupid pun, but I have to say it, the sky is the limit. Meaning, how about parts of the core network? And there's actually a topic in 3GPP right now looking at communication termination in the satellite itself. It's very important for resilience because, God forbid, anything happens to the ground segment, well, your satellite network and your satellite constellation can continue to work very happily, simply because parts of the core network are there. You can terminate your calls. You could even have terminal-to-terminal termination without even hitting the core network on the ground, in principle, even from the same satellite. So all of this is made possible thanks to the fact that in standardization community, you have people that at some point can manage their competences, can manage their strategies, and sometimes can manage even their egos to come to a very good conclusion, if you will. ISAC, same thing, but even more in the details of what happens where, because sensing requires the network to, if you will, sing out of tune. Because right now, the network was always about I send something and someone else receives something, and the network is aware of whoever receives something. But ISAC is about sending some signal to something which is not even a terminal. It's not even a thing, if you will. It's an object. It's a passive object. So really, it's about receiving something that you don't know you transmitted in the first place, or someone else transmitted in the first place. And it also requires creating new paradigms. For example, in sensing, you don't have just user plane and control plane. Now you have something else. Now you have what I might call data plane, which is neither control data nor user data. It's data from a measurement that comes from a passive, or results from the interaction with a passive object. So can this be shoehorned into a PDU session? Probably not, because, well, a PDU session is terminated in a place called the UPF in the core network, but the UPF has no use for measurements, so it's got to be something else. And do we want to route this via a routing function in the network? For example, the AMF in 5G terminology. Well, can the AMF really cope with this massive amount of measurements? Maybe not, considering the legacy effects, considering the inertia trend that I introduced earlier. So it all requires additional things to be made. Interestingly enough, can this functionality also be supported in NG-RAN architecture? Well, the answer is actually, why not? And actually, we have something which is starting in 3GPP, which is integrated sensing and communication in 5G networks. So you can actually do the new trick with the old dog, if you will. But of course, it's a totally different set of functionalities. It's a totally different set of specifications and protocols, or maybe not. Or maybe there's also the art of saying this can actually be done in a backwards compatible way if it makes sense to the community. So it's all about being there and deciding, not because it's a mantra, not because we like this to be this to be cloud friendly, and this needs to be AI native, and this needs to be resilient, and this needs to be green. It actually requires you to put your best mind to the task there. because I've heard so many times that we need to ditch that such and such protocol because it's not cloud friendly. And if you say it like that, it's the emptiest of statements. You really need to go down, and you need to be based in technical facts. So this is going to be the challenge, as always. I don't know whether this is 6G related or maybe not, but still, it's always the art of standardization. Thank you.
Thank you very much, Gino, for sharing insights on these two very important features. Now, continuing with NTN, maybe I will start with NTN because it seems NTN has figured in the discussion of all of you. It seems almost all of you mentioned this. So maybe I will start with you, Gino, because you have been working in NTN for long. What are the possibilities of having non-3GPP NTN as part of 6G network?
Very interesting and very provocative. First of all, when we decide, let me go back a bit. So when we decide 5G and NG-RAN protocols, there's actually a provision that you can connect a non-3GPP RAN to the 5GC, so to the 3GPP sanctioned 5G core network. And how do you do that? So one way that we did, we said this is going to be done through the standardized NG interface and NG-AP protocol, TS38413. But of course, if you take it as it is standardized, it assumes that the AMF, let's take control plane for short, it assumes that the AMF is talking to a G node B, or at best an NGE node B, a 4G base station that has been taught how to speak in 5G terms. So to reuse this protocol as it is, towards a non-3GPP compliant network, you need to provide this non-3GPP compliant network with how to interpret the various parts of this protocol, or the various information elements in 3GPP speak. So we did that by writing a new technical standard, which is called 29413, which is an addendum to 38413 that says, so if you want to speak with the same lingua franca towards other parts in the non-3GPP world, please look at this specific document that provides you interpretations and way to translate the specific information elements so that the other part in the 3GPP world can fully understand what is going on. So this is a very specific and technical and technically detailed example of how things can be done. So in principle, there's no preclusion of anything. Question is, does it make sense from a technical point of view? And it may, and from a business point of view. And that's another matter, of course. Let me also remind everybody here that there is no part of the 3GPP standards set which is mandatory, with perhaps only one exception in NG-RAN, which is slicing, which is it was very surprising. It was the only time in my career that I saw a statement such that, so that the network shall support slicing. It's a very first. The G node B shall support slicing. Everything else is optional. So you can actually build a 5G compliant base station without XN. Yes, I built, for some reason, I don't know, Massini-Com, if there was such a manufacturer. Yes, if it makes sense from a business point of view to build base stations that do not support the horizontal interface among them, yes, I could still claim 3GPP compliance. Meaning, you can also do this picking and choosing, or cherry picking, if you will, of 3GPP functionality into your own product and still claim you are compliant. Of course, to do it in a self-consistent way, you need to know what you're doing. It's not easy to do. And then you have to, I would guess you have to provide technically sound ways and justified ways of going your own way as opposed to the standardized way. Again, let me repeat, you probably know what you're doing if you do something like that, but it's not precluded. So NTN, yes, we have seen statements of systems saying we are going to provide, or we would like to provide, or we will have on the market systems that provide a 3GPP compliant UU interface, which is the interface between the base station and the terminal. But then the system is totally proprietary. And then we might or might not talk to a 5GC, or maybe we even have our own core network, our own services. Yes, it's possible. And then, of course, the UE might simply think that it's talking to a terrestrial base station, maybe a weird base station because of the timer settings that it requires me to set, obviously. But if you think you know what you're doing, absolutely. Of course, the less you come to the 3GPP table, the harder you're making it on yourself, because you're basing your implementation choices purely on the basis of the technical documents, which of course are very well written and very well documented. But the added bonus, if you come to the discussions, is that not only can you influence the discussion if you bring good technical contributions to the table, but you also get immediate feedback from probably some of the best of the industry. So yeah, I would. That's why there's only benefits in coming to the standards table and trying to work with everybody there. Thank you.
So thank you very much. I think we don't have much time, but anyway, I will just try to, at least one or two questions more. Subhash, I know Gino mentioned about network slicing, and you also talked about it. Do you think it is one of the leave the baggage features, or is it is it going to be a part of 6G in a different or new avatar? I mean, what do you think about it?
Well, Gino talked about this being mandatory, so I would not really take a strong view on that. But the key point I would say is that if you really look at the slicing attributes of it, you look into, say, EMBB cell versus URLLC cell, you essentially are creating a different base station capabilities. Yeah, technically you can slice it and then create those resource segmentation to create that. Of course, that's a great feature. The key question is that the utility that it would be bringing in. So for example, I can have EMBB and URLLC capability for the enterprise applications, where let's say industrial automation in a factory is required. Yeah, both of them could be there. But let us say that I create two separate cells, sans slicing. Is that something that I'm missing out? Those are the key. So it will be more of a utility driven in my mind. Architecturally, I think it's a brilliant solution. And there has been a lot of innovation. It's a beautiful concept in terms of resource mobilization and refactoring it for different purposes. So the concept is beautiful. What is the utility and the return on investment is the fundamental question. But yes, see, the AI was invented in 1950s and it is finding utility today. Perhaps slicing is one of those things that eventually will bring value. So I wouldn't say that leave it as a baggage, but probably innovate beyond what is there, right? That's how I would look at it with my limited understanding, because I personally have not implemented slicing. I personally have not seen this, but when I was making a base station, I realized how difficult it is to have the slice at the run level. So I would leave it at that for now.
Okay, thank you. Thank you, Subhash. So I think we are almost reaching the end of this slot for panel discussion. Unfortunately, I prepared a list of questions, but I don't think I'll be able to ask them. So now, thank you, thank you all, and thank you very much. We still have the question and answer session, which is essentially to take questions from the audience. And this can be addressed, the questions may be addressed to a specific speaker, or it may be, a general question. So any one of you, the experts, you can answer them. So Yeah, so maybe I give control back to Shweta, and we can go to this question answer session. I would request all of you to be there. So thank you, and let us give the control back to Shweta. Yes. Okay, so I can read some questions if you have not some unanswered questions. So there is a question here. It is from Khyati. While 3GPP has standardized IAB technology for its 5G NR standards, large-scale global deployments of 5G IAB are still in their early deployment stages. Now, as we move on to 6G, do we improve this technology in 6G, considering IAB is still being explored? Yeah, so any one of you will be happy to. It's not directed.
I can take that question. I just provided a reply to the gentleman there. So or to the lady. Unfortunately, I don't know. To basically whoever asked the question. At the beginning of my career in 3GPP, one of the first topics I worked with was relays, relaying in LTE. That was release 10. And to this day, I haven't seen any release 10 LTE relays out in the wild. So now 5G came along, and in 5G, we have standardized a lot of different flavors for relaying. IAB is just one of them. IAB, I would say, is probably the most complex one. We have IAB, we have network-controlled repeaters, which was standardized once operators got too scared of the complexity of IAB. Then we have device-to-device relays. Then we also have IoT-style relays, I think. And the latest addition is WAB. WAB is basically IAB without the CUDU added complexity. And so far, I'm afraid none of these things have been blessed with commercial success. So this is, again, something I said a few minutes back. We should watch about the hype. So once someone has a very good idea, the tendency is to say this idea will save the world, and maybe it might even replace today's network infrastructure. Chances are, if this idea is good, it will provide a very good complement to the rest of the network. And certainly relaying can provide coverage extensions and can provide maybe even capacity, but definitely coverage in some spaces which are really hard or almost impossible to reach. So then the question is, let's try to balance between standardization complexity, implementation intricacy, and business value. And topics like IAB, I'm afraid, suffer from that thing. Another example could be femtos, for example, and I could talk for hours about femtos and standardization of femtos. Thank you.
Thank you very much, Gino. Rajat, would you like to add any anything here? I mean, based on Indian experience, is IAB deployed anywhere?
So IAB is a very interesting thing. I guess Gino has already covered most of the things, but what I'd like to add is currently the deployments in the world we're seeing is the millimeter wave, where the cell ranges are quite limited in sense, and the IAB technology is being to provide backhaul and the access towards the users simultaneously. Since we have seen in the world that millimeter wave deployments are quite limited to specific country and regions, so we didn't see that the scalability or the maturity level is not being observed yet. But we look forward to that as we move towards the 6G and more, and when dense networks are being built to provide capacity and the throughputs required in the future. Probably the IAB will get mature and will more standardized with the right set of specifications and the products.
Thank you. I see some more questions. So one question, I'm not sure if it has been, but it shows unanswered. It says most of the advancement in 6G is around radio. So are there any advancement from the core network sides as well? So yeah, so any one of you would you like to answer this? Do you see any impact on the core network? I mean, in the presentations that Balazs and Gino shared, we are talking about a 5G, enhanced 5G core for 6G. Is that what? Yes, yeah, please, Gino. Yes, please.
So to be fair, we all focus very much on the RAN side,
right?
Because we heard about MIMO, we heard about potential mesh features, but we concentrated on the RAN architecture. In the vision that you heard from both, at least from both myself from Ericsson and Balazs from Nokia, and by the way, Balazs is a very good friend. We worked together. During my term as RAN 3 chairman, he was the RAN plenary chairman. So I've worked a lot with him, also during the pandemic. It was wonderful. So in both these views, we see the 6G RAN connecting to an evolved 5GC. So already there, you see more of an incremental development going on in the core network. Now, to be fair, the core network is already virtualized. It's already a service-based architecture. So those, at least from my side, and I'm a RAN guy, more of a core network guy, but as much as I see, those seem to be the most relevant recent trends. Because any other trends, for example, you might think about quantum crypto, you might think about advances in computing and things like that. When translated into the 3GPP standardization scope, they become implementation flavors. And as I explained before, once you define a logical architecture, and service-based architecture is certainly a logical architecture, of course, it incorporates and it accommodates many different ways of implementing such architecture. So you might not see, at least at this level, all the advances in technologies that will lead to different implementations, because they will still be covered and they will still be supported by the same standardized 3GPP architecture.
Pranav, if I may add a little bit.
Yes, please, Subhash, please.
Yeah.
Please.
Yeah.
Most
I think
welcome.
Gino has pretty much given the philosophical blueprint of it. So I will just say that since the 6G is bringing a set of new capabilities and usage scenarios, take the ISAC as an example, there is going to be an extension on the existing capability which Gino has already talked about. So how do you exchange the mobility information? How do you do the sensing information, right? The parallel you will have to draw. Would it be a new network function? Is there going to be a new capability exposure that you will have to bring in? Look into AI workload. Now we are talking about a lot of AI-based management and orchestration. Now the lifecycle management will involve how do you do the training management? How do you do the data collection? Is it going to be a fully self-learning network versus handcrafted machine algorithms that you would like to put in? Now, again, what is going to be the best way? Like I mentioned, that intelligence at the right place at the right proportion, right? So how would you really make sure that all of those things are orchestrated, the policies are defined correctly? Those would be incremental network functions and policies, I guess, that would be going in. But is there going to be anything earth-shattering in terms of bringing in something new? I think still time will tell. We have still time till the standardization finalizes. I am sure somebody will come up with a blue ocean strategy, but at the moment, that is how I see the outlook.
So, I would request Parag and Rajat, Dr. Bay, anybody to, share any thoughts on this aspect. Otherwise, I have a few more questions on the panel, so I can proceed. Yeah. Okay, so if no, then there is a question to Professor Abhay here. from Sonali. How does the cell-free massive MIMO architecture align with emerging 6G principles like disaggregated RAN, RIS integration, and ultra-low latency? So over to you, Dr. Abhay. Yes.
Yeah. So self-free massive MIMO by default, it supports the RAN disaggregation. How it does? So basically, some part of basement processing will be done at the access point, and some of the basement processing will be done centrally, maybe called as a DU or the CU, primarily on the DU, which we call as a CPU in the self-free massive MIMO architecture. So this aggregation allows that the processings are splitted. But at this point, ORAN architecture doesn't support the completely flexible self-free massive MIMO disaggregation. It has 8 splits, as we all know. Probably we need to bring few more splits to really get benefit of the self-free massive MIMO architecture. And also the another point that self-free massive MIMO supports is it is in a, you can see like it's a next generation for the comp feature. Now comp has a very limited addition. You can either do at a L1 or L2 level, whereas here it is more flexible. So probably some part of equalization is being done at the AP, and the remaining part of the equalizations are being done at the CPU or the DU. So which gives you a better gains in terms of throughput as well as your spectral and energy efficiency both. Regarding the last point, I think last 2 points, that RIS integration and the ultra low latency. RIS integration, RIS can be integrated with any of the networks, and it can be also very much integrated with the self-free network. So where you can see like there are few AP which are active nodes, and then RIS is more like a passive node which doesn't generate the traffic by itself, but it basically reroute the traffic to the user. Ultra low latency is something which we need to look into it. This requires a rethink in the how the frames and the data is being flowed, and through that we can manage the ultra low latency part in the self-free massive MIMO architecture. Yeah.
Thank you very much, Dr. Abhay. I have just a small question,
Yes.
maybe just lack of my understanding and knowledge. So cell, if I understand correctly, probably plays a very important role in user mobility as well. The user associates with the cell, and
Right.
because it's a mobile. So in a cell-free MIMO, how would mobility be handled? Will it have a,
Okay.
how?
So at any, I got it. So then by the name itself, like we are breaking this cellular boundary. So at any point of the time, the user may be connected to multiple cells. Now, so the handover and mobility part has to be managed carefully. So the advantage is that because you have multiple links similar to COM, and so even one link is broken down and you have a poor connectivity, you'll be still well supported through another link. So it is something like an extension of COM. The point here is that the base station of the access points are closer to the user, something like a Wi-Fi nodes. So you at any point of time, you may see that I'm receiving signals from a handful of access points.
Okay. So thank you very much. And I'll go over to the next question. This is for Parag. So, again, it is from, the question says that which emerging features or usage scenarios will likely have a significant impact on the architecture of the 6G system? So this is for Dr. Parag. Yes.
Yeah, so I think ISEC, the integrated sensing and communication. See, sensing, if we see the sensing is nothing but a kind of a radar technology. Okay, so ISEC here we are just emerging the two technologies for entirely from the different world. Okay, one from the radar and one from the telecom. So when we are merging the two technologies together, so of course there will be a totally a change at the both the core side as well as the RAN side to implement the ISEC. So I think the ISEC would play a vital role in involving the architecture from the either side, the core network side as well as from the RAN architecture side. And another this is the main one, and another what I'm thinking that as in the IMT 2030 as well, that 6G should be the AI native. So AI models, all those things that we are putting, whether it could be at the physical layer or a MAC layer or at the core side, that also defines the architecture of the 6G. So these two technology, I think that defines the 6G architecture, and it could be evolved, or I can say the different what we have seen in the 5G architecture.
Okay. Thank you very much. There is one more. I think I'm not sure if it is already answered or not. It shows it answered, but I will still ask. It is for Rajat. So it says, cellular network typically comprises of two planes, the control plane and the user plane. It has been the case for a long time. Now, do you anticipate any changes there in 6G era? Is there a possibility of adding a new plane, say a service plane, within the network itself? So that's for Rajat. Yeah.
Although I have answered the
you have already answered
query in the
okay.
chat, but the simple answer is yes. What we are seeing is a trend that apart from the control and user plane in the network, there is a need of having an additional plane. With the emergence of the services like AI native services, sensing services, the data movement, exposure to the external parties, developers, and also the compute services, which has been required in immersive communication, where the part of the compute processing will happen in the network itself. This will not be handled with the traditional controller user plane. So there will be a requirement of having an additional plane, which we call as a service plane, which helps in movement of these data, which is much beyond the communication networks or the data. So that's the crux of that, is we required a additional plane. Some people will call it as an AI plane and all, but what I call it is a service plane, which mean the convergence of the AI sensing data and the compute, and it enables the various use cases of service paradigm to AI as a service, data as a service, or compute as a service from the network.
May I add a
Subhash,
little
please,
bit here?
please.
So I will give little bit perspective, perhaps slightly differently, that if you really look at voice as an application today, voice runs as a service on top of the network capabilities provided by the current packet switch network. So in order to deliver the voice, you have a QoS attribute. So if you look into 5G quality table, QoS table 5QI, you have different categories of applications there. So let us say that today we are looking into AR/VR applications. And if you look at the capabilities brought in by IMS to do the multimedia services, the similar architecture is evolving for the low latency immersive communication enablement to happen, and 3GPP has already standardized it. Likewise, if I really look at the new emerging applications, the integrity of data plane and control plane will remain. The management plane will provide the capability to provision it. Services will be running on top of it. Now, I would look at voice as an application to be a service on top of the network capabilities provided by the network infrastructure. I would look at immersive services as a network service on top of that. Any other new application, let's say AI applications, AI workload management, also I would look. What would be important is to characterize what is the quality of service in terms of the packet delay variances you can tolerate, the minimum bit rate that you need, and that is the guaranteed bit rate that you require. If you can characterize and put in the 5QI, it probably will translate into a new capability rather than a new layer as such, so to speak. That's how I would look at it. But bringing the application closer to the network fabric, that I think is going to be a critical enabler. Like what IMS has done for the multimedia services, what the immersive communication architecture has done to the AR/VR applications. I think that is what really would matter as I see it. But that is my perspective.
So thank you very much. I think we are reaching the end of the time slot, and I would like to thank you all. If you would like to make some remarks just before we give control back to Sonali, I would request any one of you to, all of you or any one of you to make some remarks, concluding remarks, if you would like.
I wanted to just say that the keynote speakers, especially Gino and Blasius, it was great to hear you. So thank you.
I totally agree.
Thank you all for listening, and
Yes.
thanks for having me.
Yes.
Thanks for having all of us.